Okay, so now it is a problem 4 of the second sample of our final exam. Okay, so the problem asks us to find the second moment of area, so or sometimes it's called moment inertia of the shaded area here. Okay, so it is a problem examining to evaluate the second moment of area by integration. And after that, we are also required to find out the radius of gyration here. Well, how can we approach that? Okay, so now let's get it started. So again, by integration, we know that integration is actually a summation of several infinitesimal pieces. So we need to divide this shaded area into several infinitesimal pieces, right? So the way how we can divide it is, so we first can divide along x-axis, right? So along x-axis, we divide it into several infinitesimal slices. The reason why we are doing this is because now if you look at the upper bound and lower bound of these slices, both are continuous and can be expressed by one expression, right? So if you look at the lower bound, it is actually y equals to 0, and the upper bound is y equals to this expression. So that can facilitate our integration. If the expression is really complex and sometimes need a lot of effort to derive, then it means that we probably need to think about, should we divide first along y-axis? Okay. So specifically for this problem here, it should be dividing from it should be dividing x-axis first, so it will be more convenient. Well, so now as long as we divide along x-axis, so we will eventually take summation along x first, so it will be our integration on the outside. Okay, so now if you divide along y and then okay, so your integration. So now, for example, if we start from Iy, then Iy equals to, now, first it is the definition here. So the definition of second moment inertia about y-axis is, okay, it is actually the integration or area of x squared dA, right? Why it is x squared? Because when we are considering second moment of area about y-axis, it is actually integrating the square of the distance. It is a square of the distance. Okay, let me change the color here. From a specific infinitesimal area to my y-axis, which is actually the x coordinate of this specific infinitesimal area, right? So it is actually it is actually the x coordinate here. It is the reason why we're integrating the square of x here. Okay, so after we divide that, we know that the integration is of x. But now, what is the lower bound here? So the lower bound is from the origin, right? It's 0. But now, what is upper bound here? Okay, so actually the problem didn't explicitly tell us the upper bound. So we need to solve the upper bound. Okay. So now we're going to solve the upper bound as a start here. Okay. So the upper bound, actually it is our x coordinate here. Okay, it equals to what? So actually we see that both the lower bound and upper bound, they are actually the points when the curve equals to 0, right? The curve equals to 0. They are actually when we have, of course, lower bound and upper bound of x, they satisfy the curve equals to 0, right? This is a quadratic equation. Actually, quadratic equation has two solutions, right? The two solutions exactly corresponding to the lower bound and upper bound. If you solve the equation, you are going to see that x would equals to 0 or what? If, if you solve that, and you're going to see that, okay, so x could also equals to, we have 9.25 here, right? So actually, either we have x equals to 9.25 or 0. That would have my y equals to 0, meaning that our curve intersects with the x-axis, right? Those are actually respectively our lower bound and upper bound. Good. Okay. So now actually you can also substitute the solution back to the equation and to check whether it is correct or not. Good. Okay, so now we can go ahead to evaluate the integration. Good. So we go back and y equals to integration of x squared, right? Integration of x squared dA. And it is integrating. First, we divide along x, and then we integrating along x from 0 to upper bound 9.25, right? And then for a specific x, we divide along y, right? We divide along y, and that will divide a slice into infinitesimal areas, right? And for each area, if you take that out, okay, that area have y is equals to dx, and the head equals to dy. Okay, so now it is integrating along y here, right? Okay, it is integrating along y, and from where? From y equals to 0, right? From y equals 0 to where? To y is at the heart is actually on the curve, right? And y will equals to the expression of the curve, right? So the expression of the curve. Okay, so we have dy here, and it is x squared. Okay, so now to perform the double integration here, we are going to first from the integration inside, right? So we're gonna have, since it is integrating about y, but we have x squared, so it will appear to be like a constant, right? So it will be x squared times y, and lower bound 0, upper bound, it is a curve. Okay, and then dy here. Okay, now substitute the lower bound and upper bound in, you are gonna have it equals to 1.85 x to the power 3 minus 1 over 5 x to the power 4 sorry, it is a dx here. Dx. And now by performing the integration of this uh polynomial here, you are gonna see that it equals to, okay, 1.8885 over 4 x to the power 4 minus, okay, so it is 25 1 over 25 times x to the power 5. So the additional 5 in the denominator is because that we have we have another 1 over 5 from the function in the that is integrated. Okay, So now we have the lower bound 0 and upper bound 9.25, and you can go ahead and evaluate that. So the lower bound is 0, right? And upper bound is 9.25, and the result will be 1.85 times 9.25 to the power of 4, right? Divided by 4. Okay. Minus 1 divided by 25 times 9.25 to the power of 5. Okay, you are going to see that it equals to okay, it equals to 677.19. It is so the unit here. Okay, we do not have a we do not have the unit here. So if the problem tell us the unit of the problem, typically it will be the the length to the power of 4. Okay, so okay, now we have IY here, and we are further required to find KY here, and to find KY, we know that the formula of KY equals to, so the formula of KY equals to square root of IY divided by A, right? So we've already have IY, but we need the area A of the shaded area. And to find A, again, we're going to use integration. But that integration will be very similar to IY here. So A is actually integrating each infinitesimal area, right? And that would be very similar to the integration of IY, but get rid of x to the power of 2. So we will only have first integrating from 0 to 9.25, and it is of dx. And then secondly, from 0 to the curve ui. Okay, it is all we have. So by performing the integration inside, so we see that it equals to from 0 to 9.25. Okay, this becomes the regular integration. It is integrating the curve. Does that make sense to you? So actually, it makes sense because integrating the expression of a curve, it's so the meaning is actually to calculating the area underneath the curve, right? So now the meaning actually is consistent with our understanding, right? So now if we perform the integration here, we're going to see that it is actually 1.85 divided by 2, okay, x squared, and then 1 over 15 here, x to the power 3. So from 0 to 9.25, and again, so the lower bound is 0, but the upper bound is 9.25. The result will be 1.85 times square of the upper bound divided by 2 minus 1 over 15 times 9.25 to the power 3. So which is actually 26.38. Okay. Given this, we can pretty straightforwardly calculate ky equals to square root of iy divided by a. And we have iy equals to 677.919 divided by area, which is 26.38. And square root of that, you have it equals to, okay, square root of 9. It is sorry, it is a 677.19 divided by 26.38. Well, it is 5.07. Okay, so if it has a unit, so it should be, so that it should be the unit of length. Okay, so now it is actually the answer for this problem here. Okay. Okay. So this problem is actually examining evaluating the second moment of area, or sometimes it's called moment inertia, and the radius duration of of an area by integration, right? So again, so there's two things here is important. So the first thing is that we need to be clear about the definition of those and know what are the formulas that we need to use here. And the second thing that is important is that given given the correct integration, given the correct formula, how we are going to perform integration here, because you see that we need to be able to construct the integration and perform it. Okay.